Alright, so we left off talking about tangent, and let's finish tangent and get into wave properties. Properties of waves. Alright, so we notice that pi over 2 and 3 pi over 2, that's when cosine is 0, and that's when you're dividing by 0, so tangent will equal infinity at any pi divided by 2 point. And the way you'd write this is just pi divided by 2 plus pi. So it's pi times n. This might look confusing, but n is a member of integers. Alright? All I'm saying here is that it's n could be 1, it's just going to be whole numbers, basically. -1. Either way, we're always multiplying by pi and adding it to this. We could even just be adding 0 pi, so it just gets pi over 2, but that gives us an equation to connect all of these. And try it out for yourself if that doesn't make sense. But either way, at these points, when n is an integer, we get positive or negative infinity. Now, I don't know how the graph will look because these are both valid. So, let's start evaluating some of this. And then I'll go into this thing in a second. This touching line thing. So I'll turn back a page when that comes across. Alright. So I just want to find whether it goes to negative infinity first or positive infinity first. So we know the rest of the values. So sine is 0 when it hits any equation of pi. So tangent of really just pi times n. So that'd be 0 pi, 1 pi, 2 pi. 0 will be on top. Cosine will be something that isn't 0. And so tangent will be 0. So we know that this stuff will all be happening. So let's plot a few points. So let's do that same kind of graph. We know it's going to be, I don't know, it's not really going to, it's going to go past 1 and -1 because of that divide by 0 situation. But, all right, so let's do in terms of pi's. 1 pi, 2 pi. And if you forget why we keep using pi's, it's just because radians are so useful. So thinking in terms of them is best case scenario for us. So let's graph this in red. So we know it at every multiple of pi, tangent will equal 0. And we know at every multiple of pi divided by 2, so right in between, it will go positive or negative infinity. It will either go wop wop or it will go wop wop. So probably a weird sound effect for graphing, but whatever. So let's just look at this. So between pi, so 0 and pi divided by 2, both sine and cosine will be positive. So this will be increasing in the positive direction. Hopefully that made sense. So we'll get something that happens like this. And it doesn't actually touch at pi divided by 2. It goes to positive infinity. So if this goes to positive infinity, then I'm guessing this part will go negative. Let's just evaluate this. Between pi divided by 2 and 0, if you multiply these numbers, you'll multiply a negative times a positive, which will always get you negative numbers. And I didn't fill these in just because, as I said, I was lazy. And also it would be a waste of time because you get the pattern. But either way, negative times positive, so you'll always have negative numbers coming in here. And then, I'm guessing, because it hits 0, we know to just connect those lines. So over here, it goes to negative infinity. So I'm going to guess it's just going to continue that pattern. So it's a really wild function, even though it's just tangent and cosine and sine are so repetitive in a wave fashion. So that's why I predict. Let's just check like a point between pi and 3 pi over 2. Between here and here, you're always multiplying 2 negatives, so you always get positive numbers. So those would be positive. Yep, checks out. Then negatives, negative times positive. Yep. All right, and it just repeats that pattern over and over again. Past 2 pi, it'll just repeat itself, just layering over it. And that way, these functions are called periodic. They repeat each other after a certain point. So you can see this is periodic after pi. It's the exact same graph after pi. After every pi space, if you take that, now you can't even see that. Either way, if you take that to here, it's the same thing happening. So now this is what tangent looks like. This is the angle. Forgot to write that. So why is it so wild? Well, guess what? It has a close connection to the touching line, which we'll go right into. All right. And so here, this is how we constructed our first, sorry, that's sloppy. Our first unit circle. We just divide everything by r so it maintains the scale and the angle. They're practically synonymous now. And then we get x divided by r is cosine and y divided by r is sine. So that's how we came up with the unit circle. Now what if we divide by something different? Let's divide everything by x. You get r divided by x, and you get y divided by x, and then x divided by x is 1. Alright, let's draw a circle. So we know when x is 1, which will always be here, you get, what is y divided by x? That is opposite over adjacent, or the next to one. And that, if you notice, is tangent. So now we can visualize tangent. And by the way, this one, usually we got x over r. X over r is cosine, so this is 1 over cosine. Let me switch colors in just a second. So it's 1 over cosine. And by the way, that also has a name that is called secant of an angle. But don't worry about that too much. Just know that now we can also visualize secant. But here's how you visualize it. So if this is 1, this distance here will be tangent, and this distance here will be secant. Secant, tangent. And notice how we're still using the unit circle. Alright. So we have the tangent of the angle. And just to show that it goes to infinity, it always hits this line that is touching at this one point right here. Alright. Oops. So if you see right here, if we just make a line at our angle, then we keep increasing the angle, eventually this value gets really massive the closer this gets to pi over 2. And at one point it will be parallel, so we'll have no connection. So in one sense, this thing will never hit pi divided by 2, because if you keep extending this line more and more, this tangent line, it'll just keep on going off, and as soon as it hits here, the angle does, it will never be touching again. Then when it rotates again, you can just extend a line here and it'll touch way down here. You get what I'm doing here. My bad. It's just a thick line now. But you get the idea. It'll touch way down here the closer it is to pi divided by 2. Then when it rotates again, flat, it connects and then keeps going off here, and then, yeah, you can see the tan value. And that's why it's called tangent, because it connects to the touching line. You can also divide by y, see what happens, but these are the useful ones, because we can visualize all the basic functions, tangent, sine, and cosine. Alright, so now we have a pretty good understanding of tangent. Looks like this. After some point that gets all sloppy, but whatever. And I guess it repeats. Alright, so that is tangent. Making it all the same color makes it look weird. But let's just continue now. So that's what tangent is, and it connects to that line. So if you're curious, that's where it comes from. So let's move on to wave applications. So I will make a statement, and it's going to be a little bizarre. All this paper here, though. Alright, let's start in green. Okay. What if I told you most things picked up by microscopes, like light, or maybe microphones, or maybe like, either way, anything you pick up, you can pick up audio signals, stuff like that. They're all waves. Now, they don't all look like this wave, the typical sine wave. And we're just going to stick with sine through this activity. Know that cosine is the same, just that it starts at a different point. But either way, everything, like so many things around us, any kind of what we call is signal can be written as a sine. However, if you've looked at like maybe like an oscilloscope, sometimes you get weird things like this. Or you get like something like sawtooth that doesn't look exactly like it. It has something like this shape. Well, the crazy realization is that every one of these can be written as a series of these added together. And notice I said series, so just write summation of sine. Any signal in the universe can be written as this. And therefore, if you have like music, the better your device can build this up, set up this sine addition, the better it can produce a sound that's hearing. And this whole concept is revolutionary. Well, it was revolutionary during, I believe, 1800s, 1700s, 1800s. And it's called the Fourier transform. Fourier. Looks like Fourier. It's tempting to say Fourier transform. So most MP3 players and everything does this kind of thing. And it's pretty incredible. But if you don't believe me, let's try to graph some sine functions added together. But before we even do that, sorry, I know I keep delaying everything. Let's get a grasp of what different altering the function does to the wave. All right. So you get the idea. Everything can be written as an addition of sine functions or cosine functions. But notice that cosine and sine are so similar, you can actually have them recreate each other. And by the way, let's go into that, just so you can forget about cosine when you're studying this. All right, cosine of an angle. If you graph cosine, it starts at 1 and goes over. Whatever, something like that. You get the idea. It starts at 1 rather than 0. Well, at pi over 2, sine hits 1. So that means if you shift the angle over by pi over 2, it is always equal to cosine. So if you start at pi over 2 when you plug in the values, because that's what this will do. If you plug in 0, 0 plus pi over 2 is pi over 2. So it shifts this whole graph over, then you have these equal to each other. So that's all you have to do to have cosine equal to sine. Just add pi over 2 to the angle. Then if you want cosine equal to sine, just angle minus pi over 2. That equals sine. You just move it back. And so that's how you can relate these functions. And so we can just stick with sine for now because of that fact. All right. So let's get a grasp of how you can alter the function to make different shapes. So you've probably heard of this thing called frequency. Most people probably have. Frequency is just the number of oscillations per a unit. Usually the unit is time, but it doesn't have to be. Now there's also other frequencies like counting, but we're talking about just like frequencies of waves. And because light and everything can be created as waves, this has tremendous value in many, many, many fields. So let's look at how we can alter it. Let's create an arbitrary function and say it's this. And I'll tell you what each of these values will be. And we're going to use x instead of angle just because notice how we keep using this x direction as theta. So we're going to set theta equal to x because we're not using x anymore. We're just caring about changing this angle. Because this has these properties, it's very useful. And so we were working on trigonometry, triangles, but now we're working on the shape that the ratios make from the triangles, which are all around us. And then we're going to add, I know you can call all sorts of things. Let's call it y naught. Y with a 0 next to it. All right, so here's what each portion does, and here's why I named it what it is, the letter that it is. So as you change x, it will create some kind of wave. And honestly, if you alter any of these numbers, it'll just affect the wave. It won't affect the shape so much. It won't like change it into that sawtooth shape. No, you can only accomplish that weird sawtooth shape by adding equations. So let's just keep going with this. So frequency. If I increase this number, if I increase the f value greater, usually it's f is equal 1, usually a is equal 1, we're used to that. And usually that y naught value, we don't add anything to those functions usually. That's usually equal to 0. And the period, remember that when we added pi over 2, that's actually called the period. We made that 0 to start out. We didn't add anything to it. So a general sine function just has these properties. That's called the amplitude, that's called the frequency. We'll go over each one. All right, so the highest value would be 1, lowest value would be -1. And it starts at 0 because the period is 0. And it hits here at pi. It hits here at 2 pi. So forth, 0, pi, 2 pi, 3 pi. You get the idea now. All right, so if we increase f, then this angle will scrunch up, because if, let's say f is 2, all right, f equals 2 and everything else is the same. So now we have our function for angles, for waves, is sine of 2 times x, all right? So that means that at twice, it'll take half the time. I say half because it's 1 over 2. Half the time to get to these points when it's equal to 0. Because if I plug in pi divided by 2 as x, if x equals pi divided by 2, then 2 times x is equal to pi. So by pi divided by 2, this function right here, let's make it a different kind of green. This function will hit 0, I mean. So that means by multiplying by 2, we make it skinnier as a thing, less thick. So that's neat. So that's what frequency does. The bigger we make it, and if you make it smaller, if we made the frequency equal to half, then sine of x divided by 2, only when x is 2 pi, if you plug in x is equal to 2 pi divided by 2 is pi, so sine of pi would get you 0. So you'd have to get all the way to 2 pi, all the way out here, in order to make one full, just to make it over this first line. So now we made a graph that stretches much longer than it had by dividing by 2. So the bigger f is, if f is big, let's just say that, if f is less than 1, then it will be big. And if f is greater than 1, then it will be small. The distance between the waves will be small. All right, that's understood, I think. So now, period, all that does is shift where so we're continuing with this. I'm going to continue it one more video, just so we can continue with this idea. And then we'll try to add functions. I'll get out my calculator and start adding some functions, just to give you the notion of how adding functions can create any kind of shape you want if you do it right. But anyway, so we went over frequency, so that's good. So at least we did that. So we're going to continue with this in the next video. Thanks for watching so far.